Assalamu alaikum friends. I am Takdees Siddiqui with Computer Graphics for Bachelor's in Computer Science, a course being offered by Virtual University, Government of Pakistan. Today is our 35th lecture. Today we are going to start discussion on a new topic, and that is about curves. We'll take a look at different types of curves and the theory lying behind them, how to define them, and then we'll make use of those concepts to build certain computer graphics. So let's begin. We all know what a curve is. So today we will explore the mathematical definition of a curve in a form that is very useful to geometric modeling and other computer graphics applications. We'll be taking a look at what equations can be used to define curves and how they can be made use of, and then how to convert those equations into some form which can be easily manipulated when we are working with computer graphics. And easy manipulation we have learned making use of matrices. So we'll be relating equations of curves with matrices as well today. Just an idea, we have talked about polar coordinates, right? When we were having discussion on circle and on ellipses. What if we make use of the same idea, just to give it a try, since we know that we can define coordinates of a point lying on the boundary of a circle in terms of sine and cosine of the angle. Why not make use of the same idea? What if, just for test purposes only, we increment the x coordinate values in units and calculate the corresponding y using maybe sine of that theta, sine of angle, specifying a specific angle. If we can make use of this idea and calculate corresponding y values for some given x values and try to plot the resultant on the screen, we might be able to enjoy the results. The mathematics of parametric equations is the basis of Bezier, NURBS, and Hermite curves. NURBS are non-uniform rational beta splines, and we'll try to look at them as well in some later discussions. Today we will be talking about some of the basics, talking about the basic equation of curve, and then some plane curve equations, then of course relating them together and coming up with such form which can be easily manipulated like matrices. We start off with parametric equations of a curve. A parametric curve is one whose defining equations are given in terms of a single common independent variable called the parametric variable. So we'll try to come up with such equations which can be defined making use of one independent variable, the parameter. And that is why the name of these equations is parametric equations, and correspondingly the curves are called parametric curves. We have already encountered parametric variables in earlier discussions of vectors, lines, and planes. We have been talking about this very concept, so the concept of a parameter is not new to us. We have defined vectors making use of the same idea. We have talked about lines as well, parametric equations for lines, and the concept of plane was also discussed from the very same angle. In three-dimensional space, each point on curve has unique set of coordinates. Each coordinate is controlled by a separate parametric equation whose general form we have already seen. X is equal to x of u, y is equal to y of u, z is equal to z of u, which means that x is a function of independent variable u, independent parameter u. Similarly, y is a function of u, z can be expressed as a function of u. Let's mark this as the first equation of our today's discussion. where x of u stands for some not specified function as yet, which uses u as the independent variable, the one that would be determining what value x would take, independent of x's value. U would vary independently, and x would be dependent upon this value of u, and the function used would be x of u to determine the value of x for a specific value of u. For example, x of u is equal to au squared plus bu plus c, and similarly we can have for y of u and z of u. Simply, if we are going to make use of u as the independent variable, y of u could be defined as du squared plus eu plus f, and similarly we could define z of u as, say, gu square plus hu plus I. It is important to understand that each of these is an independent expression for x of u, for y of u, and for z of u, as well as when we talk about au squared plus bu plus c, they are independent expressions. The dependent variables are x, y, and z coordinates themselves, because their values depend on the value of the parametric variable u. Whatever value u takes determines what would be the calculated value for x, y, and z coordinates. So these coordinates take their values from these functions which are making use of u as the parametric variable, which is an independent variable. U is not dependent, x, y, and z are dependent upon u. Take a look. A point on a curve being defined as a vector, p of u is precisely defining a specific point lying on the boundary of a curve which is visible in the upper part, and this is not a new concept for us because we have been making use of this idea in our earlier discussions as well. So here p of u happens to be the vector that defines a point on the boundary of the curve. Now each of the points lying on the boundary of the curve can be defined by a specific vector. This is just an example. For some point p, we have p of u vector defining that point. Each point on a curve is defined by a vector p. The components of this vector are x of u, y of u, and z of u. We have already talked about these, the x of u, y of u, and z of u, and now we say that since these are going to yield values for x, y, and z coordinates, which together join hands together to form a vector like p, so we say that vector p is composed of these components, the x of u, y of u, and z of u, and we can express this as p equals p of u. Let's mark this equation as equation number 2. Now which says that the vector p is a function of the parametric variable u. So making use of the idea that x is being defined as a function of u, x of u, y is being defined as a function of u, y of u, and z is also being defined as a function of u, z of u, and all these three are forming the coordinates, the components of the vector p. We define vector p as p of u, a function of u. Parametric variable u determines the value of this vector p. Now there is a lot of information in equation 2. It's pretty simple to look at. P is equal to p of u, but when we expand it into component form, it becomes something like this. P of u equals x of u, y of u, z of u. You can see it's a row vector, and we mark this equation as equation number 3. So now we clearly see that the vector p, which we just defined as p of u, is actually the row vector x of u, y of u, z of u being all the three components of that row vector. There are only a few simple rules that we must follow to design these mathematical functions. The first of these is to define each component by a single common parametric variable. So when we are talking about these components that form the vector P, x, y, and z, they better be defined using a single common parametric variable. One parametric variable should be used to define all the three when we talk about x, y, and z. And the second rule is make sure that each point on the curve corresponds to a unique value of the parametric variable. Well, that means that whenever we have a specific point on the curve being defined with a vector, each point should correspond to a unique vector, and each vector should correspond to a unique point on the curve. So we should have each and every point on the curve defined by a unique vector, so that we can clearly tell that which vector corresponds to which point on the curve. Points on the boundaries of the curves are pretty native to us now. We have been talking about such points. We have been talking about points that lie on the boundary of a circle, points that lie on the boundary of an ellipse, and many more. So that very idea, but here the two rules that we have talked about are that number one, the components should be defined using one single common parametric variable, which should be common for all the three components, and secondly, each point should correspond to a unique vector. Each point on the boundary of the curve should correspond to a unique vector. Plane curves. The next topic that we are going to talk about is plane curves. To define plane curves, we use parametric functions that are second degree polynomials. You are familiar with the concept of second degree polynomials? Take a look at this one. X of u equals ax u squared plus bx u plus cx. Similarly, y of u is equal to ay u squared plus by u plus cy, and for z of u it equals az u squared plus bz u plus cz. This set of equations we mark as the fourth. So you can see we have expanded the x of u, y of u, and z of u, which we know are forming what? The vector p, which is going to define the point on the boundary of the circle. So these three functions, x of u, y of u, z of u, would be giving us the x, y, and z coordinates for the vector p. And these have been defined as these equations, second degree polynomials, where the a, b, and c terms are constant coefficients. We can combine x of u, y of u, and z of u and their corresponding respective coefficients into an equivalent, more concise vector equation. So we've come to know that here these a, b's, and c's terms, they are constant coefficients, and now we are going to join x of u, y of u, z of u, and their respective coefficients into equivalent, more concise vector equation, which would look like this. P of u equals au squared plus bu plus c. Now this concise equation, which is again holding a lot of information, let's mark it as equation number 5. We are going to make use of this equation later on. So keep in mind, set a pointer on it, that P of u is equal to au squared plus bu plus c. We allow the parametric variable to take on values only in the interval 0 to 1. So this u, which is the independent variable, we allow it to be changing or varying its values between 0 and 1 only, both inclusive. So u can be 0 and you can also take up value 1, and all the values in between are also assignable to u. It can generate conic curves, but it cannot generate curve with an inflection point like an S-shaped curve, no matter what values we select for the coefficients a, b, c. To do this requires a cubic polynomial. So this polynomial is not going to result in such curves that have some inflection point, like the curve S. S-like curve cannot be generated using these equations. In order to generate such curves, we'll have to move a step further and we'll have to talk about cubic polynomials. To one of the endpoints, we assign u is equal to 0, which is also a valid value. To the other, we assign u is equal to 1. On the other end, we have another valid value, because u can take up values between the range 0 to 1. So first point assigned u is equal to 0, second point assigned u is equal to 1, and to the intermediate point, the one that lies in between these two, we assign arbitrarily a value of 0.5 or half. So we say u is equal to 0.5 for an intermediate point between these 2 points. And now we can write these points as P0, P 0.5 and P1. You can see on your screens now P0 is equal to a row vector x0, y0, z0. P 0.5 is yet another row vector x 0.5, y 0.5 and z 0.5. Similarly, P1 is defined as x1, y1, z1. Now collectively, these three equations, we assign them number 6. Now remember, these three equations are defining the 3 points. The point at which we have assigned u to be equal to 0, the point at which we have assigned u to be equal to 0.5 or half, and the other point on which u is equal to 1. So P0, P 0.5 and P1, these are the 3 points where the subscripts indicate the value of the parametric variable at each point. So in P0, 0 is indicating value of u, the parametric variable. P 0.5 में जो 0.5 है, that is telling us that here the value of parametric variable u would be 0.5. And in P1, the subscript 1 is telling us that it is having u equals to 1. Now we solve equations 4, all the 3 equations that we marked as number 4, for the ax, bx, so on up to cz coefficients in terms of these points. The points P0, P 0.5 and P1 to be precise. Thus, for x at u is equal to 0 and u is equal to 0.5 and u is equal to 1, we have x0 to be equal to cx, x 0.5 to be equal to 0.25 ax plus 0.5 bx plus cx. You can see that when we put u equals 0, the terms involving u, they become 0, and hence x0 is left to be equal to cx alone. But when we replace u with 0.5, the same expression yields x 0.5 to be equal to 0.25, which is u square, 0.5 squared, times ax plus u bx, which is 0.5 bx plus cx. And similarly, when we replace u with 1, we get x1 to be equal to ax plus bx plus cx. And we can have similar equations for y and z as well. Since we've already defined them in terms of u, we know what y of u and what z of u now looks like. Making use of the same idea, replacing u with 0, 0.5 and 1 respectively, we can find the values for y0, y 0.5, y1, and as similarly z0, z 0.5 and z1. All these can be evaluated making use of the u values of 0, 0.5 and 1. Now you are looking at an illustration which shows that we have the point P0 where u is equal to 0 and point P1 where u is equal to 1, and the intermediate point P0.5 where we have u equals 0.5, and that's how these points are poised on the curve boundary. That's a plane curve defined by 3 points. Next, we solve these 3 equations in 3 unknowns for ax, bx and cx, finding the values for all the 3. You can see on your screens that ax is equal to 2x0 minus 4x 0.5 plus 2x1. bx is equal to minus 3x0 plus 4x 0.5 plus x1. And similarly, cx equals x0. Now collectively, we mark all the 3 expressions, 3 equations for ax, bx and cx to be number 8, right? So we have made use of the definitions that were there for ax, bx and cx and replacing the values for x accordingly, for x0, x 0.5 and x1. That's what we come up with. So now we have values for ax, bx and cx. Substituting this result into equation 4 yields x of u now equals 2x0 minus 4x 0.5 plus 2x1 times u squared plus minus 3x0 plus 4x 0.5 minus x1 times u plus x0. Let's mark it as equation 9. In equation 9, if you closely observe, you will be able to see that we have only replaced values for ax, bx and cx. The values that we calculated in the previous slide, those values have now been put into this expression for x of u, and now x of u is equal to, instead of ax u squared, we have value for ax replaced multiplied by u squared plus bx की वैल्यू हमने रिप्लेस कर दी है माइनस 3x0 प्लस 4x 0.5 माइनस x1, और इसी तरह से cx की वैल्यू which was evaluated to be equal to x0, that has been replaced, and thus we get this equation 9. Now again, there are equivalent expressions for y of u and z of u. Method would be the same. The very way we have computed x of u, आपने देखा ax, bx और cx की वैल्यूज इवेल्युएट करने के बाद हमने एक्सप्रेशन के अंदर उनको रिप्लेस कर दिया. बिल्कुल इसी तरह से we can repeat the same process for y of u and z of u, and we'll be able to come up with similar expressions for these two as well, and that would form the equations or sets of equations that would be defining the coordinates x, y, z of our vector p. We rewrite equation 9 as follows. We write it as x of u now equals 2u squared minus 3u plus 1 times x0 plus minus 4u squared plus 4u times x 0.5 plus 2u squared minus u times x1. And now we mark this new modified version of the equation as number 10. Using this result and equivalent expressions for y of u and z of u, we combine them into a single vector equation. As we just discussed, that the similar method can be adopted to come up with expressions for y of u and z of u, and then all the three, x of u, y of u and z of u, the defining expressions, they can be combined together to form the single vector equation, because they are components of the single vector, remember, vector p. So they can be combined to form this equation for p of u to be equal to 2u squared minus 3u plus 1 times p naught plus minus 4u squared plus 4u times p 0.5 plus 2u squared minus u times p1. Now this equation, let's mark it as number 11. Now this would be combining all the three components. The values for x of u, y of u and z of u would join hands together to form this equation for the vector p. Remember, we defined p to be equal to p of u, so we define p of u to be equal to a combination of the equations for x of u, y of u and z of u. And here you can see that the reference points p0, p 0.5 and p1 are being used instead of the components x0, x 0.5, x1 or y0, y 0.5, y1 or z0, z 0.5, z1. Now equation 11 produces the same curve as equation 5. Remember, we talked about the two equations. Equation 5, I said that you should set your pointer on it. Compare that equation 5 with equation 11. The two equations are producing the same curve. The resultant is the same. The curve will always lie in a plane no matter what 3 points we choose. That's what makes it a plane curve equation, because the curve would be lying in a single plane. The curve would be defined using 3 points, p0, p 0.5 and p1, and it would always be lying in a plane. Furthermore, it is interesting to note that the point p 0.5, which is on the curve at u is equal to 0.5, is not necessarily halfway along the length of the curve between point p0 and p1. So although u is making use of value half, for p1 we had u equal to 1, for p0 we had u equal to 0, and we said that we are going to choose arbitrarily u equal to 0.5 for the third point, the intermediate point, but giving parameter value half, u is equal to 0.5 to it, does not necessarily mean that this point would always lie halfway in the middle of the 2 points. So ज़रूरी नहीं कि p0 और p1 के बिल्कुल दरमियान में मिडिल में ये वाला पॉइंट लाई करे. It can have a different position. It might be closer to p1 or closer to p0. So it's not necessary that it is always going to be in the middle. Look at this illustration just as an example. p0 and p1, the two endpoints, and the one in the middle is p 0.5, but it is not halfway between p1 and p0. Over here you can see it is closer to p1. It appears to be closer to p1. So these 3 points are not necessarily uniformly spaced points. They can be non-uniformly spaced, the way they are appearing over here now. Now equation 5 is the algebraic form and equation 11 is the geometric form. Each of these equations can be written more compactly with matrices. As I said earlier, that we'll try to make things happen in a manner that is more conveniently manageable for us. We can work with matrices a lot easier than with the native geometric or algebraic form of equations. So now we are going to try and express them in the form of matrices. So now we rewrite equation 5 using the following substitutions. And these are that we have a row vector and a column vector. See, the first matrix is a row matrix that comprises of u squared, u and 1. There are 3 elements, u squared, u and 1, and this is a row matrix. And you can look at the right of this matrix. We have a column matrix comprising of A, B and C, the coefficients. Now what would be the resultant of the multiplication of the two? Yeah, you can recall how we multiply matrices together. The first row multiplied by the first column. We've got only one row and only one column, so when we get the multiplication result, it would be one value, and that would precisely be u square would be multiplied by a, and we are going to have au squared. Add to it the product of u and b, the second element, second in the row and second in the column, and similarly third element of the row with the third element of the column, they multiply together to give 1 times c. So as a result, what we will have would be au squared plus bu plus c. Let's mark this equation as equation 12. Look at another couple of equations. What if we mark u squared u1 matrix, the row matrix, as u, and transpose of the other matrix, the one that was a column matrix A, B, C, if we take transpose of it, it would also become a row matrix. Let's call the transpose of that matrix to be A. Mark these two equations as equations number 13 and 14. Remember, u is symbolizing u squared u1, a row matrix, and A is symbolizing what? The transpose of the column matrix of coefficients A, B, and C. And these two have been marked as 13 and 14 number equations. And finally we obtain P of u equals UA. Does that make sense? Right? Well, it does. We defined P of u to be equal to, you can recall, the u squared term and the u term and the constant, and those that we had evaluated as a result of product of these two matrices. Therefore, we can say that P of u can now be written as UA. Let's mark this as equation number 15. Remember that A is actually a matrix of vectors, right? A, B, and C, that's what it comprises of. But what are these A, B, and C? A is actually AX, AY, AZ, and B is actually comprising of BX, BY, BZ, and C, CX, CY, and CZ. Reason is that we joined the X of u, Y of u, and Z of u together. We combined them to form the single unified equation for vector P. ठीक है ना? तो जो P के अंदर coefficients हैं A, B और C, they actually come from where? From those individual equations, those that were evaluated to have the values of X of u, Y of u, and Z of u. So therefore we can say that A, which is actually ABC coefficients column matrix, actually it is comprising of a matrix that has 9 values, because each of the A, B, and C is comprising of 3 values: AX, AY, AZ, BX, BY, BZ, and CX, CY, CZ. This we mark as equation number 16. The 9 terms on the right are called the algebraic coefficients. Next we are going to convert equation 11 into matrix form. We have done that for equation number 5. Now we will do the same for equation number 11. The right hand side looks like the product of two matrices, which are the first one, a row matrix. The first element is 2u squared minus 3u plus 1. The second element is minus 4u squared plus 4u. And the third element of the matrix is 2u squared minus u. And the second matrix would be P0, P0.5, and P1. Now this would mean that we can write it like this. The P of u, as it was written in equation 11, can now be written as, or rewritten as, P of u equals a row matrix 2u squared minus 3u plus 1 minus 4u squared plus 4u, 2u squared minus u multiplied by the column matrix comprising of P0, P0.5, and P1. You can convince yourself by actually taking a product of this, and you will be able to come up with the same equation that you had in equation 11, which was defining P of U. Let's mark this equation, which is expressed in terms of matrices over here now, as equation number 17. So you see, P of U has been defined as a product of a row matrix and a column matrix. Using the following substitutions, if we replace the row matrix that appears on the left with F, we replace F is equal to 2u squared minus 3u plus 1 minus 4u squared plus 4u, 2u squared minus u. Let's mark it as equation 18, and if we replace this value of F and P can be defined as P naught, P 0.5, P1, which actually would be comprising of the individual components x, y and z at all the 3 points. So P naught would actually be x naught, y naught, z naught. P 0.5 would actually be x 0.5, y 0.5 and z 0.5, and P1 would be x1, y1, z1. Now if we make use of these two equations, the 18 and the 19, the recently made, F and P, they can be made use of, and we'll be redefining the same equation. Here P is the control point matrix, and the 9 terms on the right are its elements or the geometric coefficients. We can now write them as equation number 20. You can see it on the screens right now. P of U equals FP, whereas you know what F is, a row matrix, and what P is, a column matrix, which was defined as P naught, P 0.5 and P1, but we in actual know that each of those is decomposed or is comprising of the x, y and z components. So here we have redefined the equation as P of U equals FP. Let's mark it as equation 20. This is the matrix version of the geometric form. Because it is the same curve in algebraic form, P of U equals UA, or geometric form, P of U is equal to FP. So what should be written? Well, if they are defining the same curve, P of U is defining the same curve in algebraic form as UA or in geometric form as FP, they should be equal. We should be able to write that as FP equals UA. True. Let's mark it as equation number 21. The F matrix is itself the product of two other matrices. That we can write over here. You can see it on your screens right now. F is equal to product of a single row matrix with a square matrix, a 3 by 3 matrix. See what it is. The row matrix is U squared, U1, and the 3 by 3 matrix is, I read it row wise, 2, minus 4, 2, minus 3, 4, minus 1, 1, 0, 0. Let's mark it as equation number 22. And again I would say, in order to convince yourself, solve it. You know how to multiply matrices together. So take this as an exercise. Multiply the two matrices together and see for yourself that the resultant would be the same as is defined in our previous equation, where we defined F. I can do it for you, the first one maybe. The first row matrix would be multiplied by the first column, and this multiplication would result in 2u squared minus 3u plus 1. Got the first term? So similarly, we can compute or evaluate the rest of the two terms as well. The matrix on the left we recognize as U, and we can denote the other matrix as M. So if the right hand side matrix, the 3 by 3 matrix of the constant values, that is marked as M, so M is equal to 2, minus 4, 2, minus 3, 4, minus 1, and 1, 0, 0. Let's mark it as equation number 23. And that would mean that we can write f to be equal to um. We have defined u and we have defined m, and we have already defined f to be a product of these two matrices. So we can write f equals um. And let's mark this as equation number 24. Now using this, we substitute appropriately to find UMP is equal to UA, right? Now this is the new form that we have come up with after we equated the algebraic and the other form. Now from this equation, by pre-multiplying each side of the equation by 1 over u would result in MP equals A. Let's mark it as equation number 26. You can see that? Let's see. That was the equation. So if we multiply both sides by 1 over u, we are going to be left with MP equals A. The two u woods disappear, and we have MP equals A as the new equation, marked as the 26th. Now this expresses a simple relationship between the algebraic and geometric coefficients, which is A is equal to MP. Now if you would recall what A is, what M is, and what P is, this would start falling in place. Or we can say that P is equal to M inverse A. From the same expression, we have come up with this equation, that P, the vector that would be defining the point on the curve, to be equal to M inverse A. The matrix M is called a basis transformation matrix, and F is called a blending function matrix. So out of these matrices, the M that we have used is the basis transformation matrix. You can recall the coefficients, the constant values that we had, the coefficients, and F is called the blending function matrix. We have already introduced the concept of the blending function, or the concept of the blending. We will be making use of it pretty heavily in some of the other curves as well. So folks, that was the discussion about curves. We have initiated this today. We will be talking about some other forms of curves as well. We will be taking up Bezier curves, and we'll try to talk about some other forms of blending functions as well that can be used to define curves. But today we have introduced the concept of curve, we have talked about the equations defining curves, and we have talked about their algebraic and geometric forms, and then we have related them together as well. We were able to successfully express each of those in the form of matrices, and then those matrix forms were helping us to simplify things a lot more. And finally, when we got the two forms together, we equated them to come up with a very simple relationship, and from which we were able to come up with the simplest equation for the vector P. आज हमने प्लेन कर्व्स की भी बात की, जिसमें हमने ये देखा कि किस तरीके से हम 3 पॉइंट्स की मदद से P0, P0.5 और P1 की मदद से एक कर्व जो कि प्लेन में, एक ही प्लेन में लाई करे, वो डिफाइन कर सकते हैं. उसके फिर हमने डिटेल्स देखी, किस तरीके से हम उन पॉइंट्स को फाइंड आउट कर सकते हैं, कैसे इवेल्युएट कर सकते हैं. उन पॉइंट्स को इन टर्म्स ऑफ देयर कोऑर्डिनेट्स एक्सपैंड करके हमने देखा, और फिर हमने डिटेल से ये देखा कि किस तरीके से हर एक पॉइंट के कोऑर्डिनेट्स इवेल्युएट होंगे, और फिर उनकी मदद से हम उन पॉइंट्स तक पहुंचेंगे जो डिफाइन करते हैं उस प्लेन कर्व को. और इसके साथ हमने ये भी देखा कि अगर पॉइंट P1 और P0 जो कि हमने इंडिपेंडेंट वेरिएबल की वैल्यूज 0 और 1 पे सेट करने के बाद हासिल किए थे, उनके दरमियान में इंटरमीडिएट पॉइंट जो है जिस पे हम इंडिपेंडेंट वेरिएबल की वैल्यू 0.5 दे के रखते हैं, वो अगर फाइंड आउट करें तो ज़रूरी नहीं है कि वो पॉइंट P0 से P1 की तरफ जाते हुए ठीक आधे रास्ते पर वाक़ हो, वो किसी भी जगह हो सकता है, उसकी पोजीशन नेसेसरीली एग्जैक्टली मिडल ऑफ द कर्व में नहीं होगी, मिडल ऑफ द रूट बिटवीन द पॉइंट्स P1 और P0 में नहीं होगी. इस बात को भी हमने देखा. और उसके बाद फिर हमने नेचुरली पैरामीट्रिक जो कॉन्सेप्ट था कर्व्स का उसको हमने एक्सपैंड किया फर्दर, ज्योमेट्रिक फॉर्म भी देखी और अलजेब्राइक फॉर्म भी देखी, और इन दोनों फॉर्म्स को फिर हमने इक्वेट किया. एक आइडिया मैंने आपको शुरू में दिया था, थोड़ा सा उसके ऊपर और बात कर लें. आपको याद होगा कि जो पोलर कोऑर्डिनेट्स थे, जब हम सर्कल की बात कर रहे थे तो किसी भी पॉइंट ऑन द बाउंड्री ऑफ सर्कल के लिए हमने कहा था कि अगर हमें पता हो कि रेडियस क्या है तो हम पॉइंट एक्स वाई को इन टर्म्स ऑफ पोलर कोऑर्डिनेट्स एक्सप्रेस कर सकते हैं, आर कॉस ऑफ थीटा और आर साइन ऑफ थीटा की टर्म्स में. मेरा ये ख्याल था कि अगर आप इसी आइडिया को एक्सप्लॉइट करें और कोशिश करें कुछ इंटरेस्टिंग सी चीज़ ड्रॉ करने की. वेल, एन आइडिया कुड बी दैट वी कुड ड्रॉ साइनोसाइडल वेव और कोसाइन वेव, और वी कुड ड्रॉ टेंजेंट. इसको ड्रॉ करने की क्या सूरत होगी? आई बिलीव व्हाट वी कैन डू इज दैट वी कैन ऑन द होराइजन कंटिन्यू टू चेंज द वैल्यूज ऑफ एक्स, और उन नई एक्स वैल्यूज के लिए हम कॉरेस्पॉन्डिंगली किसी एक स्पेसिफिक डिस्टेंस आर के ऊपर रखकर प्लॉट करते चले जाएं वो वैल्यूज जो हम पोलर कोऑर्डिनेट्स के जरिए से हासिल करें फॉर डिफरेंट थीटा. सो हम थीटा की वैल्यूज जो है उन्हें वेरी करते जाएं और उनके कॉरेस्पॉन्डिंगली पॉइंट्स कैलकुलेट करते चले जाएं और उनको प्लॉट कर लें. इस तरह से जब हम नेचुरली साइन ले रहे हैं थीटा का तो कुछ वैल्यूज पॉजिटिव आएंगी, देन विल हैव सर्टेन नेगेटिव वैल्यूज. नेगेटिव वैल्यूज को अकोमोडेट करने के लिए हम कोई ऐसी टेक्निक बना लें कि उनको हम स्केल कर लें टू अ पॉजिटिव रेंज, और उसको हम इस तरीके से प्लॉट कर लें जिस तरीके से कि ट्रू साइन वेव होती है. वी कुड हैव हॉरिजॉन्टल लाइन ऑन विच वी प्लॉट दैट साइन वेव, और इसी तरह से हम उसी जगह पे अगर कोसाइन वेव को भी प्लॉट करें तो वी माइट बी एबल टू अप्रिशिएट द डिफरेंस बिटवीन द टू एज वेल. द साइनोसाइडल वेव स्टार्ट्स एंड एंड्स एट द हॉराइजन, whereas कोसाइन वेव जो है that would be starting way up and would be having cycle completed within the same span but would be looking different. और इसी तरह से हम टेंजेंट्स को भी probably plot करके देख सकते हैं. Would be an interesting exercise. So those of you who might be interested can just give it a go. Just give it a try. So today's discussion we conclude over here. We have talked about the curves and we have talked about the very basics of it. We have only been touching the concept of parametric curves and plane curves and the geometric and algebraic forms of the curves. We are going to talk about more details and different types of curves as well, but that would be waiting till our coming lectures, inshallah. We'll be talking about Beziers and we'll be talking about certain other ways of drawing curves as well, and hopefully we would be able to generate more interest and create more interest in the subject, and we will be making use of these concepts to come up with some fascinating graphics. Curves not only help us draw things, but also we can make use of the curves and the concept of curves for defining trajectories of objects that need to move around. When we are talking about animating things, we could use the same concept. Like we were talking about the sinusoidal wave, so if we define the path and we use that path not to draw a line, but to define the path for an object which moves from one place to another, that could be one way of making use of the same concept. So we will be making use of these concepts in these and other different fascinating ways, inshallah, but that would wait for another couple of lectures, inshallah. So folks, let's call it a day. आज हमने कर्व्स की बेसिस जान ली हैं. डिस्कस तो हम इनडायरेक्टली पहले भी कर चुके थे. आज हमने थोड़ा सा फॉर्मल होकर के उनके बारे में, उनकी इक्वेशंस के बारे में और उनकी आपस की रिलेशनशिप और उनको मैट्रिसेस की फॉर्म में एक्सप्रेस करने को सीखा और देखा, और फिर उनकी आपस की रिलेशनशिप को स्टडी करने का हमें मौका मिला. नेक्स्ट टाइम वी आर गोइंग टू कम अप विद सम मोर डिफरेंट टाइप्स ऑफ कर्व्स एंड देयर मैथमेटिक्स लाइंग बिहाइंड देम, and then we'll talk about some of the applications of these curves as well. आज इजाजत दीजिएगा, दोबारा मिलेंगे इंशाअल्लाह. फी अमानिल्लाह.